This is Herschel Pangborn. If you don't know me, I'm going to provide a quick overview of controls and where that fits into poets. Let's see if I can get the little flare. Hopefully you can see the mouse. So our goals today are going to be to kind of talk about what controls is at a high level, review some fundamental concepts and terminology, so things like open loop versus closed loop control, what are references, error, disturbances, input, feedback, everything. And then take a brief look at some of the features of the modern approaches. We won't have too much time to go into kind of details, but hopefully at the end of the talk, we can all kind of be on the same lingo, same understanding of fundamental trade-offs in order to help us interface and work together in poets. Not worrying about too much the algorithms themselves, because that's kind of the job of the people in poets who do controls to write those algorithms, but trying to get enough shared knowledge that we can interface. So at its core, right, controls is about decision making. So we want to extract information from some physical system, plan a course of action, and then make our system perform that action. Kind of in more of the humanities, they sometimes talk about an OODA loop, which is, I know it's used in like military strategy. Right, so an OODA loop stands for observe, orient, decide, act. Right, and it's a loop. So once you act, right, you go back and you observe again, you orient, decide, act, and that kind of loops over and over and over. And that's a big part of the idea of controls. We have this kind of loop decision-making process where we look at information, make an action, perform that action, and then reevaluate. So a good example of controls is this case here. And so this is called a block diagram. It's a way in controls that we like to diagram systems. So over kind of in the right here, you see a block labeled body, right? So this would be the human body in this example, right? And our human body has some temperature, right, which is in this case an output. And our nerve cells measure that temperature, right? And then they compare it to 98.6 degrees Fahrenheit, which is the kind of the ideal, right, the goal for what our body regulated temperature should be, right? And based on that difference between the actual temperature of our body and 98.6, right, we will either sweat or we'll shiver, right? Our skeletal muscles will shiver, or we'll do nothing, right? And then that helps to regulate the temperature of our body. Now it turns out, right, that our temperature isn't constant, right? We have these disturbances that come into us, right? Like the ambient temperature, right? What we're wearing that day, or maybe the activity level. If we go for a run, we're going to heat up, right? So the job of our sweat glands and our skeletal muscles for thermoregulation, right, is to take actions which will kind of reject these disturbances that come in either because of our own activity or because of our environment in order to maintain our body temperature as close to 98.6 Fahrenheit as we can. So that's kind of a biological example of thermoregulation. And for all these components of this diagram and controls, we like to have a common naming structure. So in this case, the human body, what we're trying to control, our system, controls, people would call that the plant. This comes from the days of power plants or industrial processes where it actually is a plant that we're trying to control. Whatever the output that we're trying to achieve, right? In this case, a body temperature, we call it the output. Maybe some subset of those outputs are things we can actually measure through sensors or estimation. We have a reference, which is our desired temperature, right? And we look at the error between what's our desired temperature and what's the actual temperature. And then lastly, our sweat glands or skeletal muscles in this case form the role of the controller, right? Determining what action to perform based on that error, and they're kind of choosing an input which will hopefully reject those disturbances to our system, right? So these are all these kind of red words here are the standard control terminology for all this parts of the block diagram. And what you'll notice here is that it's only with this measurement, with our nerves that can measure our core body temperature, right? That's the only way we can react to these disturbances, right? We have to be able to compare what our reference is against what our actually true body temperature is. And that's kind of the genius of feedback, right? Because we literally have our measurements are fed back into our controller in order to take some action based on the error. And so this is something that you'll see in lots of controllers. This is this feature of feedback based on the error between desired goals and what's actually occurring at a given time. So kind of the next prerequisite, right, is the role of dynamics in controls. So in controls, one of the first things we'll almost always do is try to model our plant, right, our system, by ordinary differential equations. And the reason for this is that we want to shape not just steady state behavior or static behavior, but also transient behavior. And a great kind of example to show why this is important is if we look at just a mass spring damper, right, this little picture on the left, right, we can write down the differential equations for that, right, in terms of the damping constant, the mass, and the spring constant. And then kind of through some substitutions, we can write this as a function of natural frequency, this omega term, right, and the damping constant, right? And so again, we can write this bottom left equation, right, this is our differential equation. And it turns out that, what these two parameters are determine the transient response of our mass spring damper. So if we have no damping at all, right, we'll just oscillate forever at the natural frequency, right? And then depending on, what the damping is, if the damping coefficient is between 0 and 1, we'll get some initial overshoot from our steady state value, and then it'll kind of settle out, right? Or at different damping values, we might take longer to reach our steady state value without that overshoot, right? And it's not just, the important thing is not only where we wind up, but also how we get there. And so that's kind of one of the things we focus on in controls. Okay, so I want to carry one example kind of through the whole talk. And so kind of trying to be a little bit relevant to poets here, we'll use this example of cooling some electric device. So we're going to assume, this is some kind of power electronics, right, that generates some heat as a result of the electrical operation it performs, and then we have some applied cooling that removes some heat. So if we apply thermal energy conservation, right, we see that the rate of thermal energy storage is equal to the generated heat minus the removed heat. And we can write that rate of energy storage, right, very simply it's just a mass times a CP. Right? And then I'm going to assume that the generated heat is some function of the applied voltage and the temperature of the device. And I'm going to assume that the removed heat is some function also of the temperature and of the fan speed input to a cooling fan. Right? And so, we see we basically have three quantities that are important. They are temperature, voltage, and speed of this fan. And so we're going to write our differential equation just kind of assuming, linear relationships here. Right, as the rate of change of the temperature is proportional to the temperature itself, the fan speed, and the applied voltage. Right, and so this differential equation would be our model of the plant of our system. And you can see that, right, this plant basically has two signals coming into it. There's the input, which is what we can control, right, the speed of this fan, and then a disturbance, right, which we're going to assume our cooling system does not have control of. So our, cooling system can't regulate this voltage, right? All it can do is change the speed of this fan in order to try to respond to whatever the voltage does. And this will result in the device achieving some temperature. Okay, so here's our plant model again at the top. And let's start, right, even though we do care about transients, for a first kind of take, let's just try to govern steady state behavior. So we're going to assume that we want some temperature set point for efficient and safe operation of our device. We're going to assume that the applied voltage is constant, right? And so then we can take this T dot term, right? At steady state, T dot should be 0. So we cross that out to 0. And then we can just algebraically solve, right? Given this applied voltage and this reference temperature, what should the input be in order to achieve that temperature? All right, so that's this equation here, kind of near the bottom left. All right, so this is things are at steady state, my temperature, I just want some constant temperature, I have some constant voltage. Here's the fan speed I should apply in order to achieve that. Right, and we would call this an open loop controller. So we're not using any temperature measurements, right, on our little block diagram here on the right. There's no feedback of that temperature back into a controller or an input. All right, all we're doing is just, assuming we have a temperature goal and a fixed voltage and algebraically finding the input we need. All right, you can kind of think of this like a toaster, right? So toasters don't measure the temperature of your toast, right, or look at how burnt your toast is. There's no optical imaging to see how brown your toast is. All right, you just pop the toaster down and it has some fixed amount of time where someone who made the toaster figured out, or a given set point for how toasty you want your toast, right? Here's how long the toaster needs to be off for, right? There's no feedback, there's no measurement. So this will actually work great if we're right about the applied voltage and our plant model is perfect, right? And our fan speed is met exactly, right? So here's kind of a quick simulation result, right? We just assume that voltage is constant at 120. Right, here's the fan speed that we calculated as this middle subplot, and we start at some cooler temperature. Turns out we will eventually reach, in this case, our set point was 60 degrees. Right, so that works great. Open loop control can work great. The problem is, what if our plant model isn't exact, or there's some disturbance, the voltage isn't exact, right? What happens then? So as an example here, right, we're going to assume maybe there's some dust that's kind of blocking our airflow, and so we get basically half the cooling that we designed for, right? And so if instead of B, I substitute in B over 2, right? Instead of reaching 60 degrees at this fan speed, we reach 80 degrees, right? And this could mean that our device is not operating efficiently, or could catch on fire, or bad things can happen. All right, so this is kind of the problem of open loop control, is without any feedback, we don't actually know that what we wanted to achieve is actually being achieved. So the solution to this is to close the loop, use feedback. And so that's a big area of research and controls, is creating these feedback controllers, tuning them, certifying algorithms for robustness, to guarantee that we'll be able to kind of have nice, well-behaved behavior of our closed loop system with our controller and our device together. So we're going to start with a basic proportional controller, defined at the bottom here. Right, so we'll still apply that kind of nominal input we've calculated that we needed to achieve our desired temperature, right? But also, if there's some error between the measured temperature and our reference, right, we're going to correct our input in proportion to what that error is. So here's kind of what winds up happening. So this top subplot, right, this black line was our open loop fan speed, right? And then similarly, the bottom subplot, the black line was our open loop temperature under a perfect model. The blue line was our open loop temperature under a kind of incorrect model where our fan was blocked and we got half as much cooling, right? And then these purple lines are simulations under closed loop control for a few different values of Kp. And so what you see is that the more aggressive we are, the more we increase this proportional gain, right? We will wind up running our fan faster, right? And because of that, we'll wind up cooling our system more. Right, so we can get lower and lower temperature error as we increase this gain. All right. However, what you see is that we don't actually, in this case, drive the gain all the way to 0. Right, we can really only asymptotically approach 0 tracking error using only proportional gain. So we kind of need something extra in our controller if we really want to track exactly that temperature reference. And so it turns out that what we need extra, right, is an integral gain. Right, so that's the second term here, right, where we look at not just the error itself, but the integral of that error over time. And so as long as that integral, or as long as those two temperatures don't match, right, this integral will continue to increase and increase and increase. And so our input will continue to increase and increase and increase until that error is 0. Right? And so here we see kind of the simulation result to show you that this is working. Right? So now instead of, in the previous example, where we always, on proportional gain, have some error, right, with an integral gain as well, right, we do drive that error to 0. Our fan speed just keeps increasing until that error zeroes out. Right, so we have nice, we would call it 0 error at steady state. So basically what we've kind of discovered here, right, is what's called the PID control approach. This is a classical control approach, probably the most common used form of control in the world, and one of the simpler ones as well. All right, so in PID we correct basically in response to errors between our desired values and our true values, right? We correct proportional to error, we correct proportional to integrated error, and we correct proportional to the derivative of the error. We didn't do the derivative term in my little example, right? But you can see it's the same idea before, right? We just take the derivative of our error, multiply it by some gain, and apply it. If you go to Wikipedia, there's actually a lot of really, really nice resources on PID control. A lot of the kind of engineering effort that goes into these controllers is figuring out what should these gains be, right? What amount do I want to correct in proportion to each of these different types of error signals? And that can really affect the transient behavior of our controller. So if you look at this little video on the right, you can see that proportional control will help to bring our error close. As soon as we have any integral value, which it's doing now, right, that will bring us to 0 steady state tracking error. But it could bring us to have these big oscillations, right, earlier in our dynamics, which for our temperature example, right, it might mean that eventually we'll reach 0 temperature error. But if we have this big overshoot in our response, then first we're going to have a big temperature violation, and that might be enough to damage our device. Right? So to correct that, we can add some derivative gain, and that helps to decrease that overshoot. And so we can see here we're really regulating not just kind of steady state behavior, but transient behavior too. You also see on this table, right, it talks about what tuning each of these gains can do to a dynamic response. and it talks a little bit about stability. Right? So maintaining stability is a really important thing in controls. If you look at this example on the top right, so this is a bridge called the Tacoma Narrows Bridge. It was built in 1940 in the summer. It collapsed in 1940 in November. At the time, it was the third longest suspension bridge in the world. But what happened was when they built it, they used static analyses, right? And they didn't consider transient response. But when the wind blows, the wind has some frequency to it, and that frequency excited the resonant frequency of the bridge, and the bridge wound up collapsing just a few minutes after this video was taken. And so this kind of illustrates we have to consider, dynamic responses when we have dynamic systems if we want to make sure that they're stable. This bottom controller, right, bottom image, right, this is a controlled system where this person trying to drive a Segway, right, he's kind of a controller. And what you see is that his proportional gain is way too aggressive. He starts to go a little bit forward, and he pulls back on the handle, and then he goes back and he pushes way too far forward on the handle, right? And every time his oscillations get further and further, right, because he's just reacting too hard to these small little changes in how he feels his weight going. All right, so this is kind of an over-aggressive controller, right? And it winds up leading to these oscillations and ultimate, failure and instability. So we want to try to avoid this behavior in controls. And one way of doing that is to try not to be kind of too aggressive in our approach. We develop a lot of theoretical tools, analysis tools, a lot of math behind trying to guarantee under certain conditions that these behaviors will occur. All right. Okay. So in addition to providing kind of model error rejection, we also want to be able to reject disturbances. So here's an example. I'm using that exact same proportional integral controller that we used earlier in the case of a fan kind of not providing full cooling. But instead of a difference in the plant, in this case, I'm stepping the voltage. Right? So for 10 seconds, for whatever reason, our voltage increases by 20 volts. All right? If I just used an open loop controller and I just kept a constant fan speed, right, we would reach, again, almost an 80-degree C temperature, right? That would be 20 degrees over our reference, and that could be dangerous to our device. But if I have this controller in, right, that sees this error and tries to react to it, I'm able to increase my fan speed in response to this disturbance. And, I get a little bit of temperature error, right? But it's only a few degrees, and hopefully our device will be able to survive that, right? If we needed to, we could make our reference 55 degrees, right? And then if we get disturbances like this, even with a little bit of increase, we'd still be able to maintain our threshold of 60 degrees, right? So closed loop control provides not only, rejection of model errors, right, or changing in our model over time, but it also rejects disturbances to our system. Okay, so what we've been talking about here is feedback control, right? Kind of this red feedback controller that I have here. And when we think about feedback control, right, very common approach, it's also a purely reactive approach, right? So in this example, right, I can't reject this disturbance of the voltage spike, right, until after I get a little bit of temperature error. And so that's how things have been done classically for decades and decades. However, some of the newer, more complex algorithms, right, can not only have this reactive approach, but also take some kind of proactive ability, right? So if I had some ability to predict that this voltage spike was going to occur, right, that I was going to basically get more heat into my device, right, before my temperature even needs to start increasing, right, I should be able to know that I need to provide more cooling, right? If I know in advance more heat is coming in, I should know in advance that I should provide more cooling out. Right, and so this is what we would call like a feed forward or maybe a proactive action, right, based on some kind of prediction of upcoming disturbances to our system. And so this is something that we're using a lot for the work we do for poets, because generally for some kind of vehicle or system, we kind of know in advance what its mission is going to be. We know that aircraft follow pretty repeatable patterns, right? They have to take off, cruise, taxi, land, right? All these things happen every flight. So we kind of can predict some of the disturbances that are going to come into our systems. In particular, right, one algorithm we use that provides this proactive action is model predictive control. So model predictive control uses a model of our system, right, that same system that, the same model that we were using for the plant earlier, right, and it uses that model to predict future behavior of the system as a function of time. And then over that period of time into the future, we try to pick the inputs that optimize behavior. So we actually are kind of forecasting in the future, making a guess about what the system will do, and then trying to optimize this behavior in the future. MVC can do some other kind of nice things, right? So if we have actuator constraints, it can take those into account when it does its optimization. So maybe we have some fan, right, that is capped at a certain RPM. That's the fastest it can spin, right? Our earlier proportional algorithm, right, doesn't know that. It has no knowledge of actuator constraints, right? If our temperature keeps increasing and increasing, it's going to just keep asking the fan to spin faster and faster. Whether or not the fan actually can spin faster, right, our algorithm doesn't know. However, for model predictive control, right, at the cost of a lot more computational and complexity and analytical complexity, we actually can factor in things like knowing that we have some constraint on our actuator, some maximum fan speed, or even knowing that there is a maximum temperature that we'd like to try to avoid. But again, this is much more complicated, both in terms of kind of the computations, the processing power we need to employ these algorithms, and also in terms of kind of the analysis. Me trying to provide guarantees of robustness and feasibility, right? It's a little bit more complex, but it gets you some nicer properties out of our controller. So here's an example. This is from a paper that I've written that is comparing these kind of traditional purely reactive controllers to a reactive controller like a model predictive controller. So in the top here, right, this is, in this case it's a heat load, but it's the same as the voltage we were using earlier. This is our disturbance. All right, this middle subplot is showing the temperature of our device, and the bottom subplot is showing our a mass flow rate, kind of like that fan speed. So you can see in our reactive approach, right, it's only after the heat load comes in, our temperature starts to increase, and then a few seconds after that, we start to try to cool off the system. All right, so that's reactive, and the result is that we get a pretty big temperature spike in our temperature. However, a proactive approach, right, we kind of know that this heat load is coming on in advance, and because of that, we start cooling down our system before the heat load ever even occurs. And thanks to that proactive capability, right, we're able to regulate the temperature much better. So this is kind of gearing more towards the things that we're working on for poets. So on that, I'm going to kind of conclude a few things that we don't have time to talk about, but are important to consider and think about. Right, estimation is one. So I can't always measure everything I'd like to control. You can think about for like a two-phase cooling system, right? Vapor quality is something that's pretty hard to measure, but that might be important to my system. It might be a dynamic I need to account for. So sometimes we need models to also predict what's happening so we can take control action, not on things we measure, but on things that we estimate. Another one is multi-input, multi-output systems. So, here we have one voltage, one temperature, one fan, but in an aircraft, right, you might have hundreds or even thousands of different inputs, different fan speeds and pumps and actuators, right? Or you might have temperatures all across your device, voltages, obviously every component, right, has its electrical operation. So trying to govern systems, not just get one output to be well behaved, right, but get all outputs to be well behaved becomes a very complex problem. In order to solve that problem, sometimes rather than have one single controller that kind of does everything at once, we might try to break that controller up into multiple controllers that communicate. And that's what this figure on the right is showing. Each of these circles, right, is a different control algorithm that's responsible for governing different behaviors of the system at different time scales, maybe at different levels of fidelity. And so that's something that we're looking at a lot for poets for these kind of large complex systems. We talked a little bit about robustness, right? So trying to guarantee that for voltage spikes of certain sizes or temperatures, certain ranges, that will guarantee analytically, mathematically that our systems are stable, that they'll satisfy constraints. And then, we can get into more complex systems, like systems that have discrete switches, on-off, instead of systems that have, continuous behavior in time. That adds a lot of mathematical complexity. Okay, so kind of main takeaways, right? Control is pervasive not only in engineered systems, but in nature. There's a difference between open loop and closed loop control. You don't always need closed loop control, but it is necessary for a lot of engineering devices that we can't model perfectly or that are subject to significant disturbances. We talked about some of the terminology of feedback control, references, inputs, disturbances, outputs, all those good things. And then we touched a little bit on some of the specific algorithms that we're looking at for poets, things that do feed-forward, model predictive control, constraint handling, a little bit about distributed controllers and why you would need those for complex systems. So those are things that you'll see, down the line.